Now we're going to look at how we can find the powers of complex numbers. And before we do that, I'm going to look at if we had z equals r cosine theta plus I sine theta. If we have this as our complex number, and if we had z squared, if we wanted to square this number, then that means we need to multiply this out twice. So we would take r cosine theta plus I sine theta, and we would multiply that by r cosine theta plus I sine of theta. And we said that if we're going to multiply these together, the rule that we just learned in the previous videos, we're going to multiply r times r, so that would be r squared. And we know that because here we're multiplying the exact same r value, so r times r is simply r squared. And then we said we're going to add the angles, so both of these angles are the same, so that's one theta plus another theta, so that would be then cosine of 2 theta plus I sine of 2 theta. And then of course if we went to find z cubed, then we would have to multiply this out 3 times, so that means we would actually then end up with r times r times r, so that would be r cubed, and then we would have the cosine of 3 theta plus I sine 3 theta. So maybe you can see a little bit of a pattern here, and that's going to lead us to our formula that says if we have a complex number z raised to a power of n, we're simply going to take the r value and raise it to that power, and then we're simply going to take the angle and multiply that by the power. So that would be the cosine of n times theta, and then I sine of n multiplied by the angle theta. So therefore, this here is a way that we can find our powers, or the exponents of our complex numbers, very quickly. And this is referred to as de Moivre's theorem, named after the mathematician. Okay, so once again, if we have a complex number raised to a power, you're just going to take the r value, raise it to that power, and then you're simply going to multiply the angle by the power, and that would be taking z to some power. So if we look at an example, what if we were given 2 plus 2i? So notice here though, the complex number is in standard form, where here our complex number was in trig form. So this de Moivre's theorem only works if the number is in trig form. So you probably guessed then that we need to change the standard form here into trig form. And you may think, well, couldn't I just use it in standard form? Well, if this is 2 plus 2i raised to the 6th power, then if we were to do this by hand in standard form, that means we would actually have to take 2 plus 2i, 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 and 2 plus 2i. We'd have to multiply this 1, 2, 3, 4, 5, 6 times. So that means you'd have to use the FOIL method here, the FOIL method here, and here. Then we'd have to multiply those 3 numbers together. So that would take quite a bit of time. So first, we're going to change this standard form to trig form. And we've done that before. It's the same way. We need to calculate the r value, and r is going to simply be the square root of 2 squared plus 2 squared. So that would be equal to the square root of 8, or that would be the same as 4 times 2, so the square root of 4 would be 2 square root of 2. And then we need to find the angle theta, so that means the tangent of theta would be equal to, we have the 2i and the 2, so that would be 2 over 2. And then we would use the inverse tangent, and 2 over 2 is simply 1, so we would take the inverse tangent of 1, and what's the angle going to be? One mistake I did make here is I always like to find from the beginning, if we look at our standard form is 2 plus 2i, where is that complex number located? Well, that says we're going to go over 2 and then up 2, so it's located here in the first quadrant. So therefore, when I go to find the angle, we know that our angle has to be in the first quadrant, so we're looking for this particular angle here, and we know that that's going to be equal to 45 degrees because the inverse tangent of 1, where is the y divided by x equal to 1, and that's going to happen at 45 degrees in the first quadrant. So what that means is we now can write this 2 plus 2i in trig form, and the r value here is 2 square root of 2, and then we would have our cosine of 45 degrees plus I sine 45 degrees. Now keep in mind, this is our complex number, but now we need to raise this to the power of 6. So this is all raised to the power of 6. So now what's the formula say here? Well, De Moivre's theorem says we're going to take our r value, which is the 2 square root of 2, so 2 square root of 2, that's going to be raised to the 6th power, okay? And then we're going to take the cosine of 45, so that's going to be the cosine of 6, the exponent, multiplied by the 45 degrees, plus I sine, once again, the exponent 6 is going to be multiplied by the 45 degree angle. And there we're going to end up with our complex number raised to the 6th power. So here we have 2 square root of 2 raised to the 6th power, and if you want here you could just enter that into the calculator, or we could work this out. That's going to turn out to be 512, and then 6 times 45, that's simply going to be 270, so that would be the cosine of 270 degrees plus I sine of 270. And this here is the trig form of our answer. So if you want the answer in trig form, this would be the answer. If we want the answer in standard form, we would have to go another step further, and we would actually just have to multiply this out. So we would have 512, and then we take the cosine of 270. Well, the cosine of 270, where is 270 located? Well, 270 degrees is located here at the bottom of the circle. So what is the coordinates there? Well, the coordinates are 0, negative 1. So the cosine of 270 is going to be equal to 0. And the sine of 270 is going to be a negative 1. So that would be plus a negative 1i. So we have 512 multiplied by this number. So 512 times 0 is 0, and then the negative 1 in 512 is a negative 512i. So this means there's no real part, it's only the imaginary part, so that would be a negative 512i would be the standard form. And we can certainly see that because over here, negative 512, if we were looking at plotting that, that would just simply be on the, well, remember this is the real axis, this is the imaginary. So this is down on the imaginary axis at a negative 512. That would be the location of this number. So you can really see the advantage here. It takes a little bit of time to change the standard form into trig form, but still in the long run it's going to be a lot easier than trying to multiply this out 6 times. And particularly if this happened to be 10 or 20, you wouldn't want to have to multiply this number out so many times. All right, let's try another example. And you can maybe try this one on your own if you want to. we have 4 multiplied by 1 minus I squared root of 3, and we're going to raise this to the third power. Now notice the only thing raised to the third power is the complex number. The 4 out front is going to be multiplied by the final answer. So once again, the first step is we want to locate where is this number located if we were to graph it. Well, we're going over 1 on the x-axis, and then we're going to go down on the y-axis. So we know we're going to be roughly over here in the fourth quadrant. So that way we know what the angle should be. So we know we need to calculate here what is the r value. Okay, so that's going to be equal to, again, the square root of 1 squared plus negative square root of 3 squared. And that means we would end up with 1 squared is 1. The negative square root of 3 squared would be 3. So the square root of 4 is equal to 2. And then, of course, if we want to find the angle, that's the tangent of theta is going to be equal to a negative square root of 3 over 1. So if we use the inverse tangent, that would just simply be the inverse tangent of a negative square root of 3. So where is our y value divided by x going to give us a negative square root of 3? Well, we know that we're looking in the fourth quadrant because that's where we're locating down here. And if you look in the fourth quadrant, you would actually find the coordinates of 1/2 negative square root of 3 over 2, because if you take negative square root of 3 over 2 divided by a half, you're going to multiply by the reciprocal of the half, which would be 2 over 1. The 2's are going to cancel, and we would get a negative square root of 3. And that's going to occur at a negative pi over 3, okay? Or instead of a negative angle, if we went all the way around, so instead of going here a negative pi over 3, we could start and go all the way around this way. And if you look on the unit circle, that would be a positive 5 pi over 3. And if you prefer at this point, instead of using the radians, you could certainly use degrees, and that means the negative pi over 3 would be at a negative 60 degrees, or we could use a positive 300 degrees. Okay, so whether you want to use, in this case, the radians or the degrees is perfectly fine. Since we did the other example up here in degrees, we'll work this one out using radians. So let's look at the original problem. We have 4 multiplied by the number. So that means here we're going to end up with 4 multiplied by our number. Well, r is 2, so that means we would have 2 multiplied by the cosine, and I'll use the, instead of a negative pi over 3, I'm going to use the positive 5 pi over 3 plus I sine of 5 pi over 3. Now, and this is where we have to realize all of this, now don't distribute this 4 yet, because all of this, remember, has to be cubed. It's all raised to the power of 3. So this then is to the third power, except for the 4. The 4 is on the outside. That's because notice up here the 4 is on the outside as well. So now we're going to use de Moivre's theorem, and I'm going to simply bring down the 4. And then we know that we're going to take 2 cubed. So here we're going to end up with the 2 cubed. So that would be times 2 to the third power. And then we're going to take the cosine. And remember, the angle here is 5 pi over 3. We're going to multiply 3 times 5 pi over 3. And we'll do the same thing over here because we're going to have the exact same angle. 3 times 5 pi over 3. So then out front here we get 2 cubed, which would be 8, and then 4 times 8 is equal to 32. And then we would have the cosine here. Notice when we multiply by 3, the 3's are going to cancel out. So we're simply going to be left with 5 pi, and then I sine of 5 pi. And here we actually have our answer in trig form. And if we want to change this to standard form, we would just take and figure out 32 times what is the cosine of 5 pi. Well, if we think about where is 5 pi located, and you could use the calculator, or we know that this is 0, this is 1 pi, and if we keep going around, this would be 2 pi, 3 pi, 4 pi, so 5 pi is actually going to end up right over here. And we know that the coordinates are -1 and 0, so therefore this is your x, this is your y. The cosine, the x value then would be a -1, and then the sine is going to be 0, so that would be plus 0i. And then we simply multiply this by the 32, and we would have a -32 plus 0i. So in this case, there is no imaginary. We only have a real number, which would be a -32. And this here would be our standard form. So here we found a shortcut. If you're looking at taking a complex number and raising it to a power, then the easiest way is to have your complex number in trig form. Therefore, it's much easier than if you have the complex number in standard form.